Cool, this barely fits on the bench. Suzuki Omnichord OM-84 from the System 2 series, as they called it. Made in 1984, but that's not the reason it's got its name, as I first thought. It's actually because by any combination of these buttons, this can produce 84 chords. Now, this isn't going to be a video about what the Omnichord is and how it works. There's lots of videos already all about this, and if you're watching this, you may already know. You may also be aware that these are getting fairly scarce, and I wouldn't say rare, because I believe they sold fairly well, and they're not hard to find by any stretch. But they've kind of gone into that collector market, I think because a lot of people on YouTube have been doing videos about them, and they've become a bit of an influential thing. And accordingly, the prices have skyrocketed over the past few years. I was interested in one of these a few years ago, and even then I looked at the prices and went, it's not for me. But like everything else that I get, I always watch the listings for broken things, and this one turned up and I still had to pay quite handsomely for it. But this had been, as many Omnichords probably are at some point, a victim of battery leak damage. I get the impression, especially going by the condition of this particular example otherwise, that these were bought in the early 80s, played with a couple of times, and then shoved back in the box for 10 or 15 years. Most people who did that forgot to take the batteries out of them. So while you may find one that's externally virtually immaculate, you may find them that, of course, the batteries leak and cause carnage inside. So this one is fully working, and it was rescued from battery leak damage. The only item I've ever fixed where the battery leak damage had done an entire lap of the insides. I'll try and include some photos, and I've just had to prop this up on a piece of tape just to get it in shot and get it out of the glare of the light. As I say, it's so big. But after restoring this and playing with its original features, I and many other people who pick up these earlier models of Omnichord always desire something that they don't have, and that is a MIDI output. Suzuki didn't make a MIDI-capable Omnichord until the third version, I think it was the OM-300 model, in 1989, and it was a completely different architecture. It was all digital, it was ROM-based sounds, as many keyboard instruments of the time were. It does provide MIDI out by the strum plate, of course, and the chords. But the earlier versions, like this one, and the OM-27 in particular, don't have the MIDI feature, but they're the more desirable and more common models to own. Trying to find OM-300s is very, very difficult, and any that do come up at a pretty high price. So wouldn't it be great if it was possible to fit MIDI to an OM-84? Well, look what we have here. So after restoring this, I had a bit of a chip on my shoulder about how much I'd had to pay for it, as I'm sure anyone who's recently bought one does, and I wondered about expanding its capabilities. I've been fitting MIDI interfaces to a few things lately. My Moog synthesizer, my Moog Rogue, that I repaired in winter of 2020 and 2021, I fitted a MIDI interface to that. And although I designed a circuit board for that, I actually modified someone else's existing circuit diagram and used their Arduino code, which had been posted publicly on GitHub. So it was a fairly quick process to do that. Earlier modifications I made to other instruments, like my Mattel drum machine, were a completely custom designed and built interface. So it got me thinking about the possibility of adding MIDI to the OM-84. I thought it would be one of those things where you'll find them easily online. Someone will have done it with an Arduino or something. There'll be loads of people who've done a simple circuit for this. You can get the schematic, build a board, and off you go. Turns out no. I was really surprised to find that when I just did a basic search for Omnichord OM-84 MIDI input mod or MIDI interface, I couldn't find anyone who'd done it. Well, after 3 months of developing this one, which I'll show in a moment, I kind of understood why. It's not been the easiest thing to do, not been the most simple and straightforward thing to do. But this particular Omnichord OM-84, which currently may be the only one in the world, is capable of reading chord data from any of the buttons, any of the 84 chords it can produce, and sending MIDI output notes from the strum plate. In the process of doing all that, I decided to go one step further with this. Most of the mods I've done up to this point and the circuit board designs, I only started designing circuit boards in 2019. So I've been getting a few things wrong along the way and slowly getting better at it. Usually when I do a kind of modification for myself, if it comes and it's got a few errors and mistakes and there's a few little bodges and things I've got to do, well, I'll live with it. I'll maybe do a couple of bodge wires, cut a couple of traces. As long as it works, as long as it basically functions for what I intended it to do, I can live with it. Sometimes some of the modifications that I make can be difficult to fit, quite involved. The Mattel drum machine, again, I had a few people asking me about that and then backed away when they realised it wasn't simple at all. With the modification that I've made for this one, I've worked really hard on this to try and make the actual fitting as simple as it can be. My aim with this modification was actually to be able to offer it as a kit. Anyone who's already got an OM-84 will be able to fit this kit with not a lot of fuss at all to their own and get a MIDI output on there. Now I must address the elephant in the room. This is of course an OM-84. There was a very similar model from the same series as System 2 called the OM-36. Looks exactly the same apart from some cosmetic changes like I think the colour. But it's limited to only the 36 physical buttons. You can't do combinations. As far as I'm aware, they are electrically the same, but I haven't seen a specific diagram of an OM-36 to absolutely confirm that that the architectures are identical. I have every reason to believe they are for cost reasons, but I can't guarantee that. Now the OM-27, which is the previous model, I believe it was around 1981, quite often you find them in brown. That uses a completely different architecture to what the OM-84 uses. So the board I've created at this moment, I've called it the MidiChord-84 because it's specifically for the OM-84 in the way it interfaces with the architecture. In the future, I may look at doing an OM-27 compatible MIDI interface. Because the architecture is different, a substantial amount of the way it works is also different. So it would need extensive redevelopment and I'd have to get hold of an OM-27 in order to reverse engineer and work on, of course, the interface. This currently is the only one I have. They don't grow on trees. Again, they're getting very expensive, so it's not something I'm in a mad rush to run out and buy unless it was worth it. But anyway, enough jibber jabber. Let's open this up and show you the interface that I've created and how it fits. So here we have it. This is the main MidiChord-84 control board. This is a wiring harness that taps into the strum plate triggers. If you touch the strum plate on the back, the trigger pulses come down this ribbon cable, and this wiring harness that connects to my board taps into those pulses. So as well as going into the main board, they come into my board as well. Down here we can see the control board and MIDI input board, which runs again along the wiring harness into the main board there. This cable, which I've just connected, solders to one point on this board, and that actually pulls a reset pulse to start the main microcontroller when you turn on the power. You may be wondering how it interfaces to the main circuit board apart from this one. There are two elements to it. The first is the trigger pulses, but they don't send the notes and the chord data. What actually sends the notes and chord data is on the back of the board. If I pull this up, it's actually connected to the board, the main Omnichord board, by a couple of rows of pins, if you can just see those, and a couple of sockets. I won't go into the crazy detail of how this works in this video, partly because I'll be giving a lot of it away, but I'll just go this far. This is the main microcontroller for the Omnichord for this model, and this is a timer chip with 3 outputs. This main microcontroller sends instructions down a data bus to this chip to generate 3 notes for every chord that it creates. Now you may be wondering, that's okay for a major or minor, but what about a 7th chord? Well, it cheats. Because this has only got 3 voices, whenever you select a 7th chord, it drops the 5th. So you always get the 1st, 3rd and 7th of the chord. But this data bus has a couple of these pull-up resistors. These are what we call sill resistors, resistor packs, which are a single unit of resistors that are all connected at one common end, and then every individual output are on the remaining legs. And these are really common to be used across data buses because they save space and complexity. And what I've done with this, and this is all you have to do, apart from drilling the case, all you have to do from an electronic point of view to fit this board is remove 4 of these resistor packs. There are 2 down here at the trigger end and 2 here at the data bus end. And I've designed this board to have exactly the same spacing with these pins. You remove the resistor packs, replace them with sockets, then the resistor packs that you've removed go onto my board. What this allows us to do is sit across that bus and monitor it and watch the data that is being sent from the main microcontroller to the timer chip. But instead of interpreting it as timer instructions, it interprets it as a table of MIDI notes. This then does some maths to work out the full range that the Omnichord can do, which is 13 notes on the strum plate. So you get the bottom octave, and then it calculates all the notes above that, and then the very top note, which it matches the root, but it's 5 octaves up. And that's essentially how this works. Every time you press a button, it watches the data that comes from the microcontroller, interprets it, and then listens for the pulses that come from the strum plate and turns those into MIDI triggers that send MIDI data out. It doesn't affect the actual Omnichord itself. It doesn't remove the Omnichord sound. The Omnichord still works exactly the same, and they're completely independent. The sustain control on the Omnichord for the actual Omnichord sound does not make any difference to the MIDI. It only controls the Omnichord sound itself. So on my control board, which I'll show in a little more detail in a minute, there's an independent sustain control which changes the note length that the actual trigger, that the actual strum plate sends of the MIDI triggers. There's also, because with different MIDI instruments, sometimes they work in slightly different ranges or slightly different octaves. There's also an Octave Shift control, again completely independent of the Omnichord itself. It only affects the MIDI, so you can select the range in which the MIDI notes are actually sent, so you can bump them up or down. This trigger board here is literally just a plug. It works in exactly the same way. So I've replaced 2 of the sill resistors here with sockets, and then those sill resistors that were formerly there are now on my main board, and this just connects straight in. So the reason I've done this is to make this as simple as possible for anyone who wants to actually fit this to their Omnichord. They've only got to desolder 4 parts, take this board, solder a wire there, make some holes there, route the wiring, plug it in, and it's done. It'll take you considerably less time than 3 months. So this is all based on an Atmega 328P. It was coded in Arduino. I've never done Arduino coding this advanced before. I'm a total beginner at programming, but I just went through the reference manual for weeks and weeks and picked away at this. Actually working on the data bus required a logic analyzer, and I had to do tables and tables of data and compare it and work out what was actually going on to reverse engineer it. There are a couple of mistakes on this board. This is my first run of the board, and there's a couple of cut traces and a bodged wire underneath where a minor routing mistake on one of the chips was made. But what I want to do is, I've already fixed this in the design, so what I want to do is a second run of these with some corrections to be able to offer this as a kit. I'm not sure yet. It depends on demand ultimately. I'm not going to be doing hundreds and hundreds of these, but it depends on demand whether I build them and ship them out at a certain cost as a ready-to-fit kit, or whether I just fit the surface mount components, for example, which are only SOIC standard, so they're not that difficult to do. They're not really, really tiny. Or whether I sell it as a board and all the separate parts, or whether I sell it as a board and a bill of materials and give away the code. There is a programming header for the code on here, so although this chip is socketed, that was only for prototyping purposes, because this is the first time I've ever done a programming header and I wasn't absolutely sure I got it right, but I did get it right, so it does work, so that was a just in case. The other concern during the build was that although there's actually quite a lot of room inside the Omnichord, you never quite know until you actually get the thing and start building it how much height clearance you've got under the casing. Luckily it turned out not to be too much of a concern. Initially, because of that, the pins that I used for the connections are the very small and thin round pins, which are a bit shorter than DuPont connectors, for example. Are very, very common. They're pretty sturdy, but they're also, when you consider the actual plug that goes on top, they're actually quite tall, and that was a concern with this, that it might not fit if I use DuPont headers. I could have just used a DuPont plug here and just crimped it. The only reason I did an actual circuit board was because it was actually cheaper, easier for me to do, and I hate crimping. It always goes wrong. It was actually easier to fit connectors to a small circuit board and have this made, and then solder up my wiring harness, which just has loops that go through, just to make it stronger than it was to actually sit and crimp connectors, which I hate doing. I have a crap experience of. So that, again, just once you've soldered the socket in, makes it a lot easier just to push in. That actually is the only bit that the height clearance is a little bit touch and go on, so I may make a further modification to this. Also, you may have spotted, if it's reflecting in the light, yes, a lot of the flux is still on the board. None of this has been cleaned yet. I'm going to get a little ultrasonic cleaner and some flux remover, I think, to try on some of these boards. But as this is in progress, really, it's working, but it's still kind of at the beta stage, if you like, and before I'm completely happy that I can put this out as a kit. Here's a closer look at the board, and you can see I had to make a couple of cutouts and things like that in the shape, just to get some clearance around the existing connectors and components that were already on the board. It actually fits and has plenty of clearance without really too much fuss. There's a couple of disc capacitors at the side that I just had to carefully just bend out of the way a little bit, but it clears everything underneath with no fuss, so that's not a problem. What I may experiment with is probably just putting a small piece of non-conductive foam on the back of the case so that it would just hold this down, but I don't think, short of throwing this around, I don't think this is going anywhere. It does rock a little bit, but again, that's maybe something that I will finesse in further revisions of the build. So I think what we should do next is take this to the studio and plug it into a few things and give a demonstration. Okay, so here we are. Full disclosure, I've completely forgotten to bring the 12 volt battery that I've been running this from the entire time, so I've had to run it from a 9 volt Boss pedal power supply. It will power it because internally it's regulated to 5 volts. Only the amplifier circuit and some of the trigger circuit runs from 12 volts, so it's a little bit touch and go, but hopefully it will demonstrate exactly what it does. So, of course, the stock Omnichord sound with its own sustain control, usual thing, But if I turn on the synth on the computer here, I've just put this into Logic just to demonstrate first of all. As you can see, it's sending MIDI. Now, what I said about them being independent. As you can hear, the one on the computer is very short in decay, and the one in the Omnichord is very long. But if I turn the control at the back, we get a longer note. So this is a variable control that starts with an incredibly short note and goes right up to, I think, about 2 seconds, and it's continuously variable. The other control on the back is in its central position at the moment, I believe. Yes, it is, and that's an octave control. So again, a rotary control, but it can actually change the octave. We can go up. So that's really useful for, as I mentioned earlier, different MIDI instruments that have slightly different ranges. When I was building this and sort of prototyping this, I noticed that the kind of range of the Omnichord sound didn't always match the expected range of the MIDI. So pretty early on in the project I decided to give it a variable transpose control, if you like, but it just shifts the octaves. One slight issue with this, and I'm hoping to revise this in the code, is that this is happening a lot today, maybe because of the lower voltage power supply, is it's prone at the moment to stuck notes. And I think I've found out what triggers it. It varies also again by what MIDI device is connected to. Yes, that's an example of it. If I play a double and it doesn't have time for the note off message to come through, it locks. So most of the time it's fine, but tap one note, it's fine. If I tap 2 notes, it gets stuck. Again, it doesn't seem to do that on every MIDI device that I've connected it to, but there's something in the program loop there that's losing, I think it's losing a note on message. I can prove that by hitting record and watching along the bottom. It's fine, no problem. I'll turn the instrument off. If I turn that back on, no problem, the notes are all coming through short. But if I double tap one and then stop it, see, we have actually got some stuck notes there, they've come out really long. So it's missing its note off or velocity 0 message on some double notes. And it was doing it a lot less when I was trying it the other day. It was working quite well, but today it's doing it a lot on this. So again, it might be down to the lower voltage, that it's missing some of the triggers turning off slightly. It might be just that this double issue was causing a conflict in the code. I also wondered if changing chord while the note hasn't turned off, before the note off message has caused it. So that may be something that I can put right with an all notes off control in the interrupt stage. What happens in the software is when I press one of the chord buttons, it triggers an interrupt on the Arduino, and that interrupt contains a line of code that polls the bus for the chord data. But I can put anything I want in that interrupt function. So I could send an all notes off message that if there are any locked notes, when you change chord, it makes sure that they're all turned off before you trigger the next one. Also, there is an option on the board for a sustain pedal. There is a socket there ready, or a header I should say there ready. I didn't fit a sustain pedal to this particular one because the positioning of the boards internally is quite critical because it's very close to the speaker. And I was unsure until I really did it how much room exactly I would have for a 1/4 inch jack socket for a sustain pedal, because a 1/4 inch jack socket is of course quite deep, because a 1/4 inch plug is quite deep, it's about 1 inch deep, so it takes up quite a lot of space, much more than say a 3.5mm 1/8 inch jack. They're much shallower, so they're much easier to internally fit than a 1/4 inch socket. So I put 2 headers on there just to allow for the option of mounting it kind of left or right of the main control plate, just as a separate socket if need be. But I didn't at this point build it into the actual panel design because I wasn't completely sure where it would best fit, if at all. So I would probably consider that an option. If you want an actual sustain pedal jack input and it just sends the MIDI sustain command, then you can mount that wherever you want. If you're not bothered and you'd rather use the sustain pedal on the instrument you're connected to, you could do that if you want. Again, it only affects the MIDI, doesn't affect the Omnichord itself. So you're probably wondering by this stage, why on earth have you gone to this much trouble for an Omnichord? They're certainly not to everyone's taste. A lot of people find them really cheap and cheesy. I don't agree. I think they're actually beautifully built. The quality of the plastics and everything on there is lovely. Of course, they're built to a standard, built to a cost, built to a market that was going to buy them in the 80s, of course the early 80s. It's all kind of part of their charm to me. There are things on the market I would consider that are much cheaper and nastier now than even this was at the time. And in terms of its playing interface, it's so unique. If you were to convert other instruments to MIDI, other keyboard instruments for example, as a controller, you don't really get anything new from them that an existing standard keyboard layout wouldn't give you. You may have your reasons for giving it MIDI input, but in terms of a control interface, I find the Omnichord is unique. And of course the MIDI implementation and the version that Suzuki did, well, it didn't come along for 8 or 9 years. So from the beginning I just wanted to make this more useful for the money I'd paid for it. But actually I found it really charming, and I think, of course, it's early days in some of the code, there's some bugs and things I've got to work on, but as a working unit at this stage, I'm really happy with it. I'm really glad I took the time to work on the boards a little more and make the actual fitting as simple as possible. Doing the actual fitting of the control board and the fascia board on the back there was quite tricky. There's no way really to simplify that other than making some kind of guide or jig, which I could do. But I would love for this to end up, as I've said, as a kit, maybe with full instructions, that could be as simple as possible for someone to fit to their existing Omnichord, because I'm sure there's lots of people out there that would love to be able to expand upon what this can do without actually taking anything away from it or carving it up or kind of destroying it. One thing I'm also quite proud of is that I'm aware of, for instance, the folk tech modifications for the Omnichord, which quite extensively transforms it into a new instrument. One criticism I've heard about that is that it takes up the battery pack. The mods that they've put in actually take up the battery pack space, and on this one it doesn't. You may have noticed in the earlier footage I had to remove the actual battery contacts in mine because they were completely corroded, so I removed the two little circuit boards with the springs and the wiring, but the actual battery compartment is still wide open. Now, I'm not ever likely to put D cells in this, because who would use D cells in anything these days? They'll cost a fortune. But it does leave me that space open to potentially put a lithium ion conversion in there, for example, so it could be again completely portable. The actual board, the Atmega chip and the logic chips in there pull very, very little current, so I wouldn't imagine that it would really make much of a difference on current draw. Anyway, if you're not using the amplifier, if you've got this turned down, then the amplifier is probably the most current hungry thing in the entire unit. But in terms of what's on the 5V rail, it's just the, of course, the internal logic, so it shouldn't make really much difference to battery life or anything like that. Alright, so I've done enough talking. You know what this is, you know what it does, you know it's in development, you know it might be available as a kit. All great. I think we should end by doing one of my favourite things with it, which is combining the rhythm and the auto bass section with an external sound. So instead of the strum plate controlling, as they call it, the sonic strings, we're going to control this a Moog Rogue. If I just shield the light from that, you can probably see as I strum it, the MIDI light comes on. So let's have a little bit of a play with this, and maybe I'll put together a little montage of some of the prototyping stage and the breadboarding stage that looked like something that Scotland Yard might have seized, and have a look, see what you think, and hopefully I'll do a follow-up on this soon when things are a little more ironed out. If anyone's got any questions or anything they want to know, fire them away in the comments, and I'll see if I can help out. Thanks for watching.